The purpose of this project is to properly demonstrate the effect of friction on both rough and smooth surfaces. Okay, let's see how this Mousetrap car deals with friction. The car went 12.5 meters with a rough surface. Now let's see how far it goes with the smooth surface. Off the tracks we go. It managed to go 22.8 meters track-wise. So what exactly happened? Well, we all know that according to the conservation of energy, the initial potential energy gets converted to the kinetic final energy. But that's only in a physician's dream world. Our textbook problems. In the real world though, there's friction. Let's calculate the percent of energy that was lost due to friction. I'm going to calculate the potential energy first. And no, it's not just as simple as mgh. We're dealing with elastic force in this case. So start by attaching a Newton meter to your mousetrap. Get a protractor and have a friend tell you when you've gone up 10 degrees, pushing the Newton meter all the way to 90 degrees, and record Newton force every 10 degrees. One thing to keep in mind is to keep the Newton meter perpendicular the whole time like shown in the picture. Now we need to figure out the distance that the arm traveled throughout the degrees. Since we're dealing with the circular motion, we need to use geometry. First step is to measure the radius. Grab a ruler and measure the metal part of the mousetrap, which mine turned out to be 5 centimeters or 0.05 meters. Now we need to take the ratio of the circle every 10 degrees and multiply that by the circumference formula. That would give us the distance it traveled each 10 degrees. Now chart a force distance graph and extrapolate it to 0.14 meters. 0.14 meters is the distance that the mousetrap arm could travel, which is 180 degrees. Now calculate the area under the graph, which would give us work, and work is the change in potential energy. Now that we have the potential energy, it's time for the kinetic energy. The mass of the mousetrap car weighed to be 0.064 kilograms. To find velocity, we would need to use the following kinematic formula. For the distance, I don't use total distance as Vf would be 0 over there. Instead, I use the distance that the mousetrap car arm dropped and reached its maximum velocity. Rearrange the formula for Vf and solve it to get a velocity of 0.87 meters per second for the rough and 1.64 meters per second for the smooth. Put those numbers back into the kinetic energy formula to get 0.0242 joules for the rough surface and 0.086 joules for the smooth surface. Now using the conservation of energy formula, solve for Q for each one. Rearranging for Q gives us 1.17 energy transformed to heat for the smooth surface and 1.24 energy transformed to heat for the rough surface. Now to find the percentage of energy that was lost due to friction, we have to take the Q and divide it by the potential energy initial, which we derived from the area under the force distance graph. And then we multiply that value by 100%. For the smooth surface, the energy lost due to friction was 73%, meaning 27% of the energy was actually kept. For the rough surface, the energy lost due to friction was 77%, meaning only 23% of the energy was actually kept. I wish I had access to areas that had a lot more differences in friction with each other, but despite that, we can still see that friction affected the car a lot.